Scientists announced they achieved fusion ignition, but nobody turned on a single light bulb. In late 2022, a lab in California fired the most powerful laser ever built at a target the size of a peppercorn, and for a tiny fraction of a second, it got more energy out than the laser put in. That's ignition. But that's also only one small piece of a very long puzzle. Fusion is the same process that powers the sun. Two light atoms, usually forms of hydrogen, get squeezed together so hard they merge into a heavier atom, and in the process, they release a burst of energy. The tricky part is that getting them to merge requires incredible heat and pressure. We're talking temperatures above 100 million degrees Celsius, hotter than the core of the sun. At that point, the hydrogen isn't a gas anymore. It's a plasma, a kind of superheated soup of loose electrons and nuclei flying around at enormous speed. The challenge has always been keeping that plasma stable long enough for the fusion reactions to actually happen. There are two main ways researchers try to do this. One uses powerful magnetic fields to trap the plasma inside a donut-shaped chamber called a tokamak. The other uses lasers to crush a tiny fuel pellet from all sides at once. The California experiment used the laser approach, and ignition specifically means the fusion reactions themselves were releasing enough energy to keep the fuel hot and burning, without needing the laser to keep pushing. The fuel was, very briefly, self-sustaining. To measure this, scientists use something called the energy gain ratio, or Q. A Q of 1. G of 1 means you got out exactly what you put in. The 2022 experiment hit roughly Q equals 1.5, meaning the fuel itself produced about 1.5 times the laser energy delivered to it. That's a genuine milestone. Here's where it gets complicated, though. The lasers used to trigger that reaction consumed about 300 times more electricity from the grid than they delivered to the target. So the actual energy balance for the whole system was deeply negative. The experiment proved a physics concept, not an energy source. Think of it like this. Imagine you invented a match that, once lit, burns hotter than the flame you used to light it. That's impressive. But if it took a whole box of matches just to light the first one, you haven't solved the heating problem yet. For fusion to produce usable electricity, researchers estimate you'd need a Q somewhere between 5 and 10 just to break even on total system energy, and probably Q of 30 or higher to make it economically worth building. The gap between where we are and where we need to be is still significant. The tokamak approach, used by projects like ITER, being built in France, takes a different route. Instead of a quick laser pulse, it tries to hold a continuous plasma steady using magnetic fields shaped into that donut ring. ITER is designed to reach Q equals 10, but it won't generate any electricity either. It's still a research machine. There are also several private companies now racing to build smaller, cheaper fusion reactors using newer magnet technology and different plasma shapes. Some claim they could have working prototypes within a decade. That's possible, but fusion timelines have slipped before, so it's worth watching carefully rather than counting on any specific date. So what ignition actually means is that the fuel can sustain its own reaction. A real physics threshold crossed for the first time in a lab. What it doesn't mean is that fusion power is around the corner. There's still the engineering of capturing that heat, converting it to electricity, and doing all of that reliably and cheaply at scale. Fusion research is genuinely progressing faster now than it has in decades, partly because of better computing, better materials, and more investment. Ignition was a real step forward. It just wasn't the finish line. If you want to understand what comes next, the engineering problems between ignition and an actual power plant, that's a whole other story worth exploring.